So what I will talk about is very much connected to my, let's say, my heart, in the sense that this is I mean, an overview of a lot of work that the people have been done in mixed integer, in particular linear optimization, starting from Gomory's seminal paper in 1958, and to connect this with a lot of the activity that the chair that I was holding at Polytechnique Montreal has been working on, which means connecting this with the last but one wave on artificial intelligence, which was the revolution of deep learning and machine learning. That is already like 10 years old, more or less, while the latest, let's say, big revolution with large language models is not covered with this talk. So, part one of the talk is I'm going to run through mixed integer linear programming. So kind of saying that is a successful story. This is a typo. It's not 6075, but it's 65 only. Mathematics, years of mathematics, algorithms, and software development. In the second part, I will actually reinterpret most of the tools and the building blocks through artificial intelligence. So see how machine learning in particular has been applied for actually try to speed up this successful story, this work. And I will try to finish with some perspectives, and in particular with some challenges that I think are still on the ground. So, of course, I don't have to convince you about the importance, I think, in this room about mixed integer linear optimization or operation research in general. This is applied pretty much everywhere, pioneered by people in the audience in terms of both the use in practical applications and the theory behind the scene. This is just the pictures of where some places in which this is used. And in particular, just to give let's say, a practical perspective, this is what I will talk about today. So among the various things that you can do in say, discrete optimization, I guess mixed integer linear optimization is based on this framework. So I will talk about, I mean, I will specifically think about this as a minimization problem, mostly. Linear function over a set of linear inequalities, which is represented here from AX less or equal than B. For simplicity here, I will be using binary variables, even if this is not necessarily what the only way. I mean, of course, you can extend this to mixed integer, as I was saying, means that the variables are continuous. Some of the variables are continuous, and of course, generally integer variables, of course, extend the binary requirement. But pictorial representation here, binary is good, and the game that is played in mixed integer linear optimization or programming is the following. Assuming that you know the optimal solution, which of course is not the case, you have on the one side a trajectory, which is the red trajectory here of the primal bound. So you want to find the feasible solution and successively improving the feasible solution until you prove optimality. But proving optimality is not a primal game, is actually a dual, primal dual in a certain sense, but mostly for the solvers is a dual game that starts by solving the LP relaxation of the problem. So it means that you're solving the problem in which you're dropping the integrality requirement of the binary variables, and you're just, for example, saying that the variables are between 0 and 1. So at that point, you have an approximation, optimistic approximation of the value of the problem, so a relaxation. Since we're minimizing, this is going to be down here. And then you have another trajectory, the blue trajectory here, that is actually improving this bound, the dual bound, until the two trajectories intersect, right? Once this is actually the case, you can prove optimality, and you have a certificate in the fact that your problem has this value as the optimal solution. So the dual bound is essentially the together with the primal bound, defining what is the gap of the optimal solution of the computation. So this is time here. So by starting, we have potentially an infinite gap because we have a dual bound, but we know that primal solution. As soon as you have a primal solution, you start to measure the gap, and this gap is going to converge to 0 if you've done everything well. And the reason to have it binary here is that this can be represented into a search tree, which is given by the blue point over there, that is the optimal solution of the LP relaxation. And then after that, in order to repair the fact that once you're dropping the integrality requirement, such requirement is not accepted anymore, is not satisfied anymore from the relaxation, then what you have to do is that you have to implement, among the several things, you can implement this as branching on the variables, fixing variables at 0 and 1, and the frontier, which is defined by the open nodes, gives you the dual bound. So the best possible, more optimistic approximation among the open nodes is giving you the value of the point in this curve. Okay? So this is a more smooth, more continuous curve, while this one is a much more, let's say, stepwise function, because as soon as you improve the solution, you actually get a big, potentially big drop into the value. So this is actually courtesy by my friend and former postdoc and former member of the chair, Elias Khalil. Beautiful picture representing the entire thing that we have been struggling for 65 years just in one single slide. So, now, as I said in the first part, I will try to give you an intuition how we got there. I mean, algorithmically speaking, that was not very surprising, but I mean, the reason why I'm saying it's a successful story is that everybody in this audience has probably experienced with software that is actually solving this problem relatively well, right? I mean, Cplex, Express, Gurobi now, Skip, and more type of software. But the question is how we got into that. Essentially, I would say that the early days of mixed integer linear optimization are characterized by the effort of implementing a reliable branch and bound approach in which you're solving the LP relaxation, and you keep doing this all the time, and you embedded this into a simple branch and bound scheme. There are two remarkable exceptions. In 1983, Crowder, Johnson, and Palberg implemented a particular solver called PIPX that was actually doing pure 0-1 LP, but was already including a lot of tools that later on has been, or building blocks that later on became fundamental for MIP development. And another big step has been in 1987, the one of Van Roy and Wolsey, that with the MPS ARX had another solver that was actually very strong. But the crucial step to jump to the current, so nowadays MIP solvers, has been the one that follows a couple of papers developed at Carnegie Mellon by the group of Ballas and Cornejols, and with their student at the time, Sebastian Seria. So these two papers have the first one to show that you can do cut-in plane theory inside the MIP solvers by generating linear inequalities which are somehow, let's say, somehow generic and not particularly designed for polyhedral purposes for solving a problem. Of course, this is a generalization of what happened in the TSP context, so traveling salesman. The mother of everything here is the paper by Palberg and Rinaldi on showing that you can solve TSP instances of large size by cutting planes and branch and bound, so the branch and cut framework. But these were the two papers in which essentially the extension of the framework to the general case of integer programming. So without assuming anything on the structure of the methods A, that I've been showing before was actually pioneered. And by the way, this is an interesting paper in 1996. When I was a student in Bologna, and I'm sure Francois in the audience have done the same, when I was a student in Bologna, Silvano Martello and Paolo Tot were telling me that Gomory cats were fantastic theoretical tools, but we were not using in practice whatsoever. So this was the first paper in which this has been shown that the Gomory cats could be used in practice, and this is the place in which we have been seeing implementing into the solvers. So this picture is now, or this table is now relatively old, but as actually quite old. I think has been designed until the version of Cplex 11.0, which goes back in 2007. But I think it's still very useful to point out what it is. So 1.2 was the first version of Cplex that was able to do branch and bound. Cplex started as a solver for linear programming, so no branch and bound mechanisms, so not mixed integer linear programs. So then from version 1.2 moved to be a branch and bound solver, and that was in 1991. So 1991 to actually 2007. So there are several versions that you can see. The interesting picture that you have here is that this has been run back in 2007 on 1,734 instances for 30,000 CPU seconds. So each version of Cplex was run in this way, and this is the number of times in which the corresponding solver is actually better than the solver that at the time was the best one, so the one 11.0 to the one in 2007. Okay, so two things to do, and this time, of course, the number of words, and 0, 0 here because the comparison is the 2007 solver now. So this is also the time in terms of I mean, time with the normalized versus Cplex 11. Two interesting things to say about this table. So the first one is pointing out to what I was just describing. So this big jump from 21.30, much more time than Cplex 11, to only 7.47, which is a big jump. So the largest jump you can see here in this table happened for version 6.5. For software developers in the audience, you know that you generally don't put big algorithmic improvements on versions which are not 0.0, right? I mean, it's like 6.5 sounds like a strange number for having a big improvement from an algorithmic perspective. But what they realized back in 1999, following the paper by Seria, Sebastian Seria and co-authors, was the fact that including Gomory cats, the picture was changing completely. So they didn't want to wait for the development of the new version. They just wanted to put it out and putting a flag over this particular thing. So this is a big jump and is motivated only by the inclusion of Gomory cats into the, okay? So this was the first time in which the framework became a mixed integer solver based on cutting planes, and in particular on Gomory cats. And the other picture that I think is quite interesting, and I will come up to this. So the other information that you can get from this table is, so the solver developed in 1991 was still at the time, and I bet is still now, faster, at least 10% faster than the state-of-the-art solver on 17 instances, which sounds like magic, right? I mean, why it should be? Easy problem, perhaps. Exactly. The point is that the entire development of MIP solvers is based on a large group of problems, and one of the biggest difficulty of solving mixed integer linear programs is that in the framework, which is currently still the framework that the people are using all the time, so the framework of one model, one shop fits all. So the thing is that developing a solver that should be good for everything. Then when you implement anything sophisticated, you end up in trouble with instances which are actually easy, right? I mean, instances in which the LP relaxation is already pretty good, and just doing a nice, simple branch and bound is going to get you what you want. So I will come back to this. So pictorially, this is what I'm talking about, right? I mean, unless, except for this is a maximization problem, unfortunately. So these are the integer points. The black points are the integer points in the LP relaxation of this object here. This is the optimal solution of the LP relaxation, and this is a linear inequality that is actually cutting off the fractional solution and improving the relaxation itself. So this is called a cut in plane, a cut in plane, or a cut. And this is, in particular, in this case, I guess this is it can be seen as a Gomory. So now, in the nowadays solvers, what are the main ingredients? The main ingredients are 4, and processing, preprocessing is 1. Cut-in plane generation, we already talked a little bit about, is the second one. Branching strategies and primal heuristics are the others. So I will go through this very quickly, but I want to give you an intuition how important those blocks are. Also because they will be the blocks that in the second part of the talk, I will jump on and say, well, what can machine learning do for those blocks? Okay, so the first block that is currently considered to be the most important one is the preprocessing part. So what does preprocessing do? Essentially, it does change the initial formulation which is given to the software, the solver, by doing a couple of different things. So on the one side, it does model preprocessing, means that try to actually clean the model which has been provided by removing stuff which are definitely not useful, like redundant or quick constraints or information. Sometimes the models are coming to the solver by modeling languages, which are nice to use, but at the same time produces let's say produces model that have redundant information, constraints in which there is no variable, and stuff like this. So this is the part in which there is a cleaning, initial cleaning, and in this initial cleaning there is also collection of information. And collection of information is very useful for the algorithmic component. So these are more sophisticated parts in which you want to discover some implication and substructures that may be useful for the computation. For example, you want to find out if there are clicks that for which you can improve. Clicks means variables which are all together connected, especially binary variables. And at that point, you can strengthen the formulation in the set covering or set partitioning context by making the inequality stronger. And of course, there are plenty of this information, and this information you want to potentially fix variables by using those information, pieces of information, and so on and so forth. But technically, this is a super important component that is helping strengthening the overall process and making the formulation time. So, of course, there are, in general, it doesn't change the solution space of the problem. So it doesn't kill any solution at all. So it's saying here, generally, without changing the set of optimal solutions. In principle, however, can change the set of feasible solutions. So because you know the feasible solution already, you can discard other feasible solutions that are not likely not to be, I mean, probably not being optimal for the problem, and so reducing the solution space based on that. So cut-in planes are, I've already tried to give you, let's say, try to convince you that how much important they are. And essentially, they are based on this simple observation. Now, this is actually most of the times they are based on simple observation. So this is actually the set that I was discussing before, AX less or equal than B, X non-negative, except that is a more general set. So we're not restricting the variable to be binary, and not all the variables are restricted to be integer. So this now is the relaxation of this set in which I'm dropping the integrality requirement and I keep only the linear constraints. So P is my set. So we are interested in general purpose cutting planes that can be derived without assuming any special structure on the matrix A. Differently, with respect to what Parsberg and Rinaldi were doing, they were studying specific inequalities which were actually valid for the TSP polytope and not for in general. Then, valid TSP inequalities valid inequalities valid for the TSP polytope can be seen as obtainable in with general operations, but this is not what they were doing at the time. So what is a valid inequality? Is an inequality in the form alpha x less or equal than beta that is actually is said to be valid if it satisfies all the points in S, which is a feasible set, but it becomes a cutting plane, so something useful if satisfies all the solutions of this guy, but actually cuts off some of the solution of this guy. Okay, so rate makes the relaxation small. Okay, enhances the relaxation. So how do you obtain a valid inequality for your problem? Well, of course, there are many ways of doing this, but the tool, the engine that is going to be used, is used inside the solvers the most, is the following one. So essentially, Farkas lemma. So any valid inequality for the problem can be obtained by a set of multipliers U that are applied to the set. And then the situation is that if you are multiplying AX less or equal than B with the set of multipliers U, which is non-negative, then the situation stays the same, provided that beta is greater or equal than UB. Okay, so this is just a Farkas lemma and nothing more than aggregating constraints and finding one single inequality that is actually valid for the overall problem. So now, how do I use this simple observation this is actually for finding a valid inequality, not a cut, right? I mean, a cut is something that has to reduce the size of the solution space of the LP relaxation. How do I find a cut using this tool? Well, what I do is that I have to solve the separation problem. The separation problem for me is this. So given a family of inequalities with some characteristics, so I want to take a point x star, which belongs to P, but doesn't belong to S, so it's a fractional solution. And solve the separation means find an inequality alpha x less or equal than beta that belongs to the family, and such that alpha x star is strictly greater than beta. So it's outside of the set that I'm interested in, which is a set S, capital S. So the cutting plane algorithm works in this way, already outlined by Gomory in 1958, that's why the 65 years, and solve the problem over the LP relaxation, gets x star. If x star belongs to S, then stop. Otherwise, solve the separation problem, get again inequality, add it to the original problem, and then keep going. Okay, very simple algorithm. Gomory shown in 1958 with some specific selection of U and applying a rounding operation, which will be clear in a second, you can actually having a convergent algorithm for integer programming. Okay, for actually at that time for integer programming, so not mixed integer programming, but this has been extended roughly 50 years later by people at IBM. So the idea of the rounding argument is very simple, once again. So I'm just saying if one variable x, which is required to be integer, is I have something valid that says that is less or equal than f, and f is fractional, then I can always say that x is less or equal than the f rounded down. Okay, that's a very simple argument. And then it can be used in a more general framework saying, well, for example, in this example, if x1 plus x2 is less or equal than 1.9, both x1 and x2 need to be integer. So I know that these two guys has to be less or equal than a rounded down value, which is actually 1. Okay, super simple, except that you can apply it exactly to the framework here. where U is your favorite set of multipliers with the left-hand side, and the right-hand side, UB, becomes a fraction, right? I mean, at that point, this guy, if this guy must be integer, then this guy must be integer as well. So you take U such that the UA is actually integer, then UAX must be integer as well, and the right-hand side must be integer, so you can round it down, which is exactly what happens here. If you take these two inequalities and you take multipliers y1 and y2 equal to half, then 2x1 plus 2x2 is less or equal than 3.5, which means that it's giving you exactly this valid inequality over here, which is totally redundant for your problem. But as soon as you apply the integrality requirement, the rounding over here, you're cutting off the fractions. Okay, very simple. Except that you were going to ask me, okay, so y1, u1, u2 equal to half gives me exactly an integer left-hand side, so 2x1 plus 2x plus x2, but it's not so trivial to actually do it in general. And it's not so trivial to first define an inequality which is really tight to your current point, and then later on applying the operation. So all these pieces are easy. So how do you select the u? Gomory has shown us that this is actually very easy. You can read the U from the basis of this simplex tableau. So you get the simplex tableau, you get the inverse of the basis, and you get exactly what you want. Okay? So this is what Gomory does, and together with the selection of the variables, so applying this on a lexicographic context, so using always selecting a cut, one single cut at a time that is associated with the variable with the minimum index, and keep doing this, you have a finite algorithm for integer programming since 1958. So now, why the people didn't use it until the mid of the 90s? Because the algorithm using one single cut and doing lexicographic simplex is totally, I mean, useless, takes forever to do that. So the observation by the Carnegie Mellon people was, why should we generate only one cut and caring about the convergence property? Let's generate a bunch of cuts, one for each fractional variable, and then adding them into rounds. This was actually, interestingly enough, a way of for them to generate something which was actually added to compete with their main algorithmic tool, which were disjunctive cutting planes or lift and project cuts. But finding they as sometimes happens in the science, they found out that this one was potentially unbeatable in the practical side, because what's much easier and faster to separate. So now, branching. What do I do when I'm getting tired of cutting planes? I can do this framework for a long time in order to strengthen my LP relaxation, but I have two drawbacks. The first one is the LP becomes large, and large LPs even nowadays imply essentially computing time which becomes significant. And the second drawback is numerical issues. So I'm adding cutting planes, I'm adding a lot of cuts which are, let's say, close to the others, and then creating a huge number of fractional solutions, which mean fractional points to the polyhedron, which implies degeneracy is going to be a problematic situation at some point. So there is every solver has some work limit for which at some point you don't want to do cutting planes anymore, and then you have to start doing the splitting that I outlined in the second slide. And the splitting more generally, when there is no binary, the requirement is not binary only, then is simply to say I take one fractional variable that is supposed to be integer, and I actually split the problem in two subproblems. One by rounding the variable down and one value down, and the other one by rounding it down. Okay, very easy, trivial, And of course, you can prove that every feasible solution is in either in one side or on the other side. And you can iterate the process over and over until you have solved every single submit that is obtained in this way. So now, so this is the most trivial version, right? I mean, in a certain sense, why you should, I mean, this idea of splitting can be applied to anything. You can split by taking any combination of the integer variables, computing a value, going on one side or the other. Why is actually nowadays the solvers are pretty much only using branching on variables? Well, again, this is because this is the most efficient way of doing things. If I branch on a variable, like in the way I'm indicating here, the situation is that that particular, the next LP that I have to solve is actually totally trivial because I only change the bound of a single variable in my LP, which can be recovered by simplex pivots very, very fast. In a few pivots, I'm going to get to optimality again. Okay? So this is the reason why variable branching is still the most useful way of solving problems, even if in the meantime, solving LPs with integral point methods became actually faster than solving LPs with the simplex. In most of the situations, using an integral point method for solving one single LP is the best. But the problem is that if I do branching, I have to restart from scratch and solving the next LP essentially from scratch, which is actually just something that you cannot afford until the entire process will take several hundreds, sometimes thousands, sometimes hundreds of thousands, sometimes millions of nodes to actually complete. So, of course, then you cannot solve millions of LPs from scratch, but you can essentially change the solution of this LP over and over by simplex, very simple simplex pivots. So there are two questions behind the scene that are obvious, but I'll spend a little bit of time on those because they become very important in the second part of my talk, if I ever get that. So the first part is there are two options that we have to, there are 2 degrees of freedom. The first one is the node selection. So when I open several nodes, where do I jump first in order to make this, the blue curve that trajectory that I shown you before going as quick as possible. The second one is among all the possible variables which were supposed to be integer and are now fractional, which one I pick, right? And unfortunately, especially the second one of this question is super fundamental for having a fast convergence. And this is the place in which a lot of attention in the area of machine learning has been devoted. So just to give you an intuition, the classical choice that the people have been using is to say, okay, the variable that is closer to actually 0.5 for binary or to the middle of the fractional interval, right? 3.5 versus 4, between 3 and 4. So it is in the middle, is the variable that is harder to decide. So we should branch on that particular variable. An interesting experiment by Tobias Achterberg back in 2005 shows that this rule is as good as random. Okay? So, which is bad. Okay? As good as random means is bad. So you need to do much more work in order to get something done. And in particular, the way in which currently we understand computationally the framework is based on this idea of strong branching, which is the following. I take a variable. I take all the variables which are supposed to be fractional. Sorry, which are fractional supposed to be integer. I simulate branching on both sides. So I fix them down and up. I solve 2LP relaxation, and then I get the score, which is given by the improvement in both nodes, combination of the improvements on both nodes. And I'm going to branch on the variable, which gives me the highest improvement. What's wrong with this idea? Yes. So it takes a lot of time, right? I mean, potentially, every variable is fractional. So it means that n variables, 2 LPs per variable, 2n, and I have to solve 2n LPs. Yes, I told you that, but just changing one bound is fast. But still, I have to do pivots for 2n sub-problems, and for every one of the nodes, which is totally impossible. So this is the place in which a lot of attention from the machine learning, let's say, interaction. When we started to have interaction with machine learning has been concentrated. So can I do strong branching faster? The way in which the problem is solved currently is a combination of strong branching and so-called pseudo-cost branching, which is the idea of saying, well, I can, if I already did strong branching on a particular variable and I already branched on that particular variable in the past, likely the variable, I can measure how good the variable was, even if I'm branching on the variable somewhere else in the tree. It's a very wild guess, but practically it works. Final building block. 20 years, there was a tremendous improvement on the capability of the primal heuristics of mixed integer programming solvers. Just to give you an intuition, this is Skip, the best currently MIP solver, non-commercial MIP solver. This guy has as many as these balls heuristics. So heuristics are algorithms that try to convert a feasible fractional solution into an integer solution, hopefully improving the current solution. And in this case, they are called diving heuristics or rounding heuristics and so on and so forth, or they actually apply large neighborhood search. So they take an integer solution, which has already been found, and they try to improve it by local search by adding an inequality or fixing a certain set of variables in some way. And recursively calling the software again. So, which is kind of surprising because in order to improve your current solution, you are actually solving another NP-hard problem, which internally, with of course some working limits and so on and so forth. But still, it kind of shows on the one side how important heuristics are, and on the other side, how mature the technology is, because internally you can call the technology itself in order to obtain other things. Interestingly, a very nice experiment by Emily Danna back in 2006 says that even if I actually give the optimal solution value to the MIP solver, so if we, actually, let me go here, so I think I have a picture. Let's go back to this. Even if I tell the solver that the optimal solution is this one, so I remove completely the upper part of this object. So I just needed to converge on the blue part to the optimal solution value, because I know that that is the value. So I just want to prove optimality. The speed up of the MIP solvers is up to 2. So I can cut the computing time down of a factor of 2, which is not, I mean, it's nice, of course. Whenever we obtain it in practice, in our framework, we are happy, but technically it's not even 10, right? I mean, it's like, it's not even an order of magnitude faster. So in a certain sense, this shows that we're not doing great in terms of the algorithm itself. So the bulk of difficulty is proving optimality. And on the other hand, it shows, however, that most of the MIP solvers are used as heuristics, in the sense that if you are able to produce a very good feasible solutions, users are most of the time happy. Okay? They don't want to necessarily find optimality. I mean, I do like it to find optimality, but in practical applications, it's not always necessary to do that. So let's jump to the second part of the talk, which is the challenges and opportunities provided by artificial intelligence. This is about the last, let's say, 10 years. And of course, has been motivated by the incredible success of deep learning, in particular on many fields of applied fields like image recognition, language processing, sequential games, and so on and so forth. So then the question became obvious, natural to ask. So can you use those techniques in order to speed up the framework that I just gave? As I said before, this is the last but one revolution that we have seen. The last one is the very recent large language models. Many of us have been start thinking about how to use those, but I don't have anything to report about the context of speeding up the process that I described before using large language models. And I don't know if I'm the right person to do that. But schematic overview. So in the last 10 years, this is what I mean, this is picturing a nice picture slide from my friend Neil York Smith that is actually trying to capture what is going on at the intersection of machine learning and combinatorial optimization with all building blocks of people doing really a bunch of different things. This is covered in two nice surveys, one coming out of this of this chair with our former student Antoine, and another one, a very nice paper by the group of Pascal Van Entering. So in particular, the activity has been running around, a lot of activity has been running around this concept. So so the machine learning people didn't trust us or our people. And so they said, well, maybe we can just solve the problem without those people like me. And so I take the problem definition, I actually replace it with a machine learning framework, and I produce the optimal solution. So can I, well, optimal, let's remove all. So it's a statistical method, so I can produce a feasible solution, maybe. So this is the framework which is called end-to-end learning, and has been pioneered in a lot of interesting papers starting in the middle of 2010, especially on the TSP as usual, because that's the easiest playground in which you can play with. The feasibility of the problem is trivial to test, so which is a big thing for artificial intelligence because it's a statistical method. So making sure things are feasible is not obvious. Of course, you give up optimality completely. So if you ask me, that's not a particular promising area of research because, I mean, I would say that if Francois sits for, and many other people in the audience are sitting for, let's say, a decent amount of time, they will come up with a good heuristic for any kind of combinatorial optimization problem, being better than this kind of heuristics. However, the interesting thing is that by doing this, the machine learning community and the people that have been working with them, they came up with nice architectures that later on has been used in more interesting, let's say, areas, research areas. So I will not go any further on end-to-end learning. I'm not a big fan, as you can imagine, as you can now just realize. What I will go a little bit more in details is this part of the picture that I've shown you before, with, let's say, an addition of another block, which is learning to configure. So the idea is what we call the machine learning augmented combinatorial optimization, or MIP. So which is the idea of saying, I want to use machine learning in the 4 building blocks that I discussed before. Okay, so how can I use machine learning for making those blocks better? Okay, this is the result. I mean, whatever I will talk about today is in a nice survey that I co-authored, and it's the work of Lara Scavuzzo, which was actually was a visiting scholar here at the chair, and which is you can find in this archive paper, likely in the MPB. I mean, I will talk about only this part in my keynote talk at ISMP 2020. So again, this is the picture that we are playing with. And there are two questions that we have started to look from the very early days, and in order to make the solvers better. So the first question is, there are components in the part that I described to you, which are just take too long, right? I mean, strong branching is one of them. So it's a good, let's say, algorithmic framework for doing a branching, but we just cannot afford to do it because it takes too long, as Sebastian was pointing out. So the question behind the scene is, can I learn strong branching? So can I do strong branching without really computing all these LPs and essentially approximating the score branching, strong branching score, or in any case, seeing which variable is we want to branch on. The second one is there are situations in which even if our software and our algorithmic framework is exact, so we want to go to optimality, still we make a bunch of decisions in a very heuristic fashion. So we don't understand the mathematics behind this. Okay, let's try to be honest. So even for branching itself, so we don't have a characterization of what is a good branch and bound tree, right? We don't know. We just have a computational evidence that this thing converges faster than another thing, but we don't know what is going to be the best way to go. And I mean, if you think about it, it's not very surprising because unless P is equal to NP, branching is necessary, right? I mean, and unless E equal to NP, the size of the branch and bound tree is going to be exponential, okay? In the worst case. Actually, thinking about this, if I have to look back at my career, I'm actually surprised more the fact that it works more than the fact that it doesn't work in all the cases. So essentially, this says that real world is actually easier than the worst case. Most of the times, the problems are actually easier to solve than what we can expect, because, for example, matrices are very sparse. The constraints that we build are very sparse, and we have been smart in strengthening the formulations and so on and so forth. So we've been doing a lot of good work, but at the same time, somehow this is a bit of a mystery to me. So two things, too long, too heuristic. And the question is, behind the scene, can machine learning methods as imitation learning, reinforcement learning, and all the recent powerful techniques in deep learning and architectures like graph neural networks, which has been pioneered here, help combinatorial optimization and in particular mixed integer linear programming to actually deal with these two things? Too fast, too slow, and actually too heuristic. And however, we need to keep those requirements in mind. So we are mathematicians, so we want to keep math feasibility, and we want to keep optimality. So we want to make sure that our method is able to compute an optimal solution, unless, and then we may not want you to do it, right? I mean, we may say, okay, I give up, but still we want to keep this possibility while we are developing the algorithms. And there have been a few methods which are, of course, been applied for doing this. One is what we call in the survey with Antoine and Joshua, learning properties. So the idea is MIP solvers are highly configurable objects, and in which the choices of which kind of algorithm you can apply depends on some characteristic of the problem that, I mean, either you know mathematically very well, or you want to learn from a practical perspective. And the idea behind the scene is to say, okay, I can use a machine learning framework. I can bypass this part and then doing whatever necessary, regularly we do. Problem definition, OR algorithm, solution. Or I can use the machine learning algorithm to actually precondition the configuration of the problem in such a way that I can actually speed up the computation based on this. And just to be more practical, this is actually the work of Julia Darpellon, which was the first student in the chair back in 2015, first PhD student in the chair. So is the older daughter, or many of you in the audience, or many people at the older sister of many of you in the audience, and I saw some in the online audience. So her work together with Pierre Bonamy at the time at Ciplex was, okay, so this is the formulation of some, let's say, connected problem to mixed integer linear optimization. So this part is still linear as before, except that it's written in equality form, but there's nothing changes here. From this part on is what we are expecting, except that the objective function has a quadratic component. Still a linear component, but it's a quadratic component. So there are two algorithmic ways of solving this problem. So solving the LP relaxation of this, the continuous relaxation of this, by relaxing the integrality variable and just to do an NLP or QP-based branch and bound, or linearizing whenever possible this objective function and solving the problem as a mixed integer linear program on a relaxation, okay? Or on a reformulation of the problem, okay? These are two ways. And this goes into the two heuristic perspective that I was discussing before, in the sense that we don't have a mathematical intuition of which one is better. We don't know. We simply don't know. So what we did is to say, okay, let's collect data, generate a lot of instances, looking at which are the characteristics of the matrix and a few other things, dynamic features, and so on and so forth, to try to decide this and implement a classifier in Ciplex. This is the first example of a machine learning algorithm designed by machine learning methods and so on and so forth to actually be implemented successfully into a commercial solver like Ciplex. And here we're saying that without going into the details, I can actually make this decision in a much more accurate way. I, of course, make some mistakes. Degradation is a statistical method. We don't know how to, we don't know the mathematics behind the scenes. So actually, the only thing that we can do is statistics here. And but still, I have a very solid improvement over this decision. So every time Ciplex now receives an input, a mixed integer quadratic optimization problem, runs the classifier, decides if linearizing or not linearizing, and then goes to the, okay? And successfully does. The learning repeated decisions is, of course, what I was announcing from the very beginning, branching. So at every point in time in which I needed to make a decision about which variable to branch on, I'm going to run my classifier, which is in this case is not a classifier, but is a predictor of the quality of a variable to be the variable to branch on, and then I order the variables accordingly, and I branch on the variable which is suggested. And this has been done in a very, let's say, a very fundamental, at least a very cited paper by Maxime Gas, Didier Chatelat, our student, Antonio Ferroni, and Laurent Charlin, which is a professor at HEC. And by using, for the first time in combinatorial optimization, graph neural networks. Graph neural networks are neural networks that are capturing very well, in a natural way, the characteristic of graphs, and in particular for us, the characteristic of a MIP. So the bipartite graph, we're thinking the MIP as a bipartite graph in which the variables are on one side and the constraints are on the other side. The connection is if there is a variable in a particular constraint. So graph neural networks are very good in capturing the structure of the MIP and understanding the various local information related to the fact that the branching on this particular variable will affect all the constraints in which the variable is bound on. And doing this, we have been, for the first time, being able, so the activity on variable selection in branching has been going on for already from the first attempts by by the group in Liège of Quentin Louveau and the group at Georgia Tech by Dilkina Bistra and her student, that by the way was Elias Khalil. And they have been doing a lot of interesting things, but they have been always playing the game of saying, can we beat a strong branching, full strong branch, which is not very reasonable because nobody does full strong branching, right? I mean, because it's too expensive. So beating a full strong branching is relatively easy. This was the first paper in which we were beating the state-of-the-art skip solver by actually doing a prediction based on the graph neural network output in order to find out which is the variable to branch on. So the two paradigms that have been applied a lot have been, of course, demonstration versus experience, which is not very surprising. Demonstration means that you have some sort of experience in this. Demonstration means you have a decision to make. You have an expert that you know how the decision is going to be made by the expert. You want to actually find a policy that minimizes the difference between these two things. And instead, the experience part is you make a decision, and instead of collecting an information over the loss function, which is associated with the difference with the expert, you collect a reward based on the quality of the information that you have produced. So this is, of course, very much a reminder of the imitation learning perspective. This one gives us the classical framework over the Markov decision process, which means the connection with reinforcement learning. So all the papers which are pretty much that have been surveyed in that particular survey that I was mentioning in the middle are actually using a combination of either one of this framework or a combination of those. So let me finish with some perspective and challenges. So this is a challenge. So this is a famous website a few years ago. This person does not exist.com. This is a face of somebody that's been built by artificial intelligence, okay? So this is a collection of random pixels. This is another collection of random pixels, but with two different outcome, right? I mean, it's like this is a person or a picture of a person. That one is a collection of random pixels. So why am I presenting this? Well, in a certain sense, it's because this is a collection of random a matrix with random IID coefficients. This is actually a matrix with also random IID coefficients, but that's following some path, some characteristics, right? And at the moment, the challenge is I cannot do anything over this. I can do things over this both in integer programming, so I needed to have a structure, and in machine learning for integer programming. So what I try to say is that I need to learn from some structure. So far, I'm not generalizing to any integer program, with a few exceptions. So for example, Fong work in Fong in the audience there. On primal heuristics, we are able to actually generalize relatively well to 0-1 problems by doing primal heuristics by machine learning. But in general, for example, for the branching rule, if I train my graph neural network to branch for set covering, and I try to use the same model trained for set covering for knapsack, is going to be a disaster, okay? Totally out of line. So we don't generalize out of distribution, which is a challenge. If you ask me, probably it's not the biggest challenge, because I feel that that the one shop fits all or one model fits all current version of Vip solver is obsolete. We should go to something else, something which is much more specific to the type of instances that we want to solve, still keeping the framework. But that's something that will bring us too far away, and Federico wants me to finish. So this is another interesting perspective, which is called decision-aware learning, or as many have decision-focused learning, or other ideas. So one big difficulty for using machine learning in optimization is that what you're using this objective function, for example, in imitation learning, this objective function of the loss function, right? I mean, you wanna predict something and you wanna stay close to the expert. But this is not the real goal of optimization. The optimization goal is to find the optimal solution or the best possible solution. So there is a disalignment between the way in which you evaluate the error that you are making in the prediction and what is going to happen at the very end with the error, how the error propagates to your decisions at the very end. So this is the way in which the people are trying to actually deal with this. So using machine learning in a sort of feedback loop, or OR in a feedback loop. So you're going to do the prediction, you make decisions, but you're using, let's say, MIP or operation researcher to actually give an information about how good the prediction is about. For example, if you want to predict the objective function or the cost in the objective function and various other ways. So this is an interesting area of research pioneered by several people, including people at Columbia, Elmachub and Grigas, and France, Axel Parmentier in France. My favorite challenge and perspective is on using machine learning for helping MIP to repeatedly solving the same problem. So this is a picture of one of the first papers that has been doing this. So there's a paper by Xavier et al. At Georgia Tech. So what they were doing is solving unit commitment problems. In unit commitment, what happens is that every day you're solving a unit commitment. So you're deciding if activating how much every power station is going to produce, but the power stations are always the same. The day is always the same. The demand simply changes for day to day. So the question is, can you leverage what you have been doing before in order to speed up the computation of the day after? Okay, and this is, I think it has been picked up as a research question a lot. There's been the competition. The MIP competition in 2003 that Cornell has won is about solving mixed integer linear programming in sort of sequence, so group of problems which are same characteristics. This is slightly different in this context because you're thinking about using the learning offline and not online. But nevertheless, this is actually a very important component that I think is potentially giving us, potentially could give us a lot. And yes, so summarizing, I think we have 3 tasks here. On the primal side, finding better feasible solution. Dual side, you will find, I mean, converging faster to optimality. Configuration task is the task of try to actually make the algorithm works better by making smarter decisions before or in the process. And yeah, I think this is giving us evidence that that improvements in the framework can be done. There is a lot more to do. Areas repeatedly solved, that's what I was talking about before. Data certainty is another one that is maybe use a lot more of statistical learning in the framework. Pattern discovery is something that we would like to have in order to speed up some heuristic decision that we're still making. And yeah, I guess this is all. Thank you.